last two sections, 12.3 with integral test, and then 12.4 with the different comparison tests, we were only looking at positive functions, or positive series. And so this will be the first test that lets us deal with certain non-positive series, or series particularly that alternate and have a positive term, then a negative term, positive term, then a negative term. And so let's just consider one here to begin with. So 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and so on. All right, so here's just good practice from back in the second section, I guess. If I asked you to write out the form of this, right, make it a sum from 1 to infinity, what goes in here? Fraction. I want the denominator, the numerators.
1 over n.
1 over n, except for the sign flips, right? And so how do we make the sign alternate? Negative 1 to the n, right? Now that's not quite right. If it's n, what do we get? N plus 1, because we want it to start off as positive, right? That makes sense? Okay, so this is almost the harmonic series, right? But it's got that negative 1 in front of it. So this will be called the alternating harmonic series. And so let's just think about the sum, this partial sums for a second. S sub 1 is 1, right? And here I'll draw a giant piece of a number line. There's from 0 to 1. We probably don't need that much of it. But S sub 1 is 1, so I'm here. What's S sub 2?
1 minus 1/2.
1 minus 1/2, so 1/2. I'm not worrying if I'm accurate there. Right in the middle somewhere, right? So that will be where S sub 2 is. What about S3? 1 minus 1/2, and then back 1/3, right? So 5/6, right? Don't worry about exactly where it is, but somewhere like this. Does that make sense? And then now let's not worry about the actual number. Where's, oh, I said S3, this was S2, right? S3, where's S4? So you're going to now subtract 1/4, right? So you're going to go back here. Is it in here or is it over here?
Between S2 and S3.
Yeah, so 1/4 is less than 1/3, right? That distance is 1/3, 1/4 is less than it. So we come back somewhere in here, right? And then when we add, or now we add 1/5 in, right? And so we move back, but we move back less than we had just moved. So S5 will be in here, somewhere like that. Does that make sense? So are we going to converge or not? Yeah, we're going to converge because we're going to keep just, I'm going to start exaggerating here. We're going to bounce back and forth like this, right? And each time we'll bounce a little bit less. And we're really just going to run out of space. There's going to have to be some nice value that we get close to. Does that make sense? So you just spring back and forth and get squeezed into one spot there. Okay. Now there's certain conditions about this, right? It required that we had a positive, and then a negative, and then a positive, and a negative. It also required that these terms were getting smaller so that you didn't go from here to here and then jump back over here, right? You have to have some consistency about the size of things. And so that's what the theorem will say, but essentially this is the proof. As long as you have the conditions of the theorem, this is going to happen. Okay? All right. And it'll also give us a nice value for the remainder, like we talked about before. But let's state a definition first, and then the theorem. So again, doesn't need to start at 1. But I'll just write it this way: the sum from 1 to infinity is an alternating sum, an alternating series. If the a sub n's look like this, they're -1 to the n times b sub n, or negative 1 to the n plus 1 times b to the n for some positive series, or some positive sequence. So again, that requires now that each term will flip from being positive to negative, positive to negative. So be careful. I mean, if you had something like this, negative 1 to the n times 5n over negative 2 to the n, right? You might think, oh, that's an alternating series because I have that, but they cancel each other out, right? And it's always positive, so it's not really an alternating series. So you're not going to see anything like that, really. Okay. So there's our definition, and then our theorem is the following. Okay. So suppose that I'm just going to write it like this. Okay, so now I have a series here where it's negative 1 to the n over b to the n, sorry, negative 1 to the n times b sub n, where the b sub n's are positive. So I have an alternating series. You could replace this with n plus 1 as well, right? It'll be the same theorem. So if you have this set up, and then you have the following: if so 1, right? So first of all, our limit, or our nth term test says that if this sequence inside here, the negative 1 to the n times b to the n, doesn't go to 0, then we'll diverge, right? So that's essentially all this is. So you first have to have the b sub n's go to 0, right? The terms go to 0. And 2, the b sub n is decreasing. Let's write it this way. B sub n plus 1 is less than or equal to b sub n. So that's the sequence. B sub n is decreasing. Okay, so if all of this is true, then the series with the negative 1 to the n in there converges. Okay, so if you have a decreasing sequence whose limit is 0, and then you alternate it instead of just keeping it by itself, it forces it to always converge. And so let's just apply it to this alternating series, or alternating harmonic series. So let me just write it out here. Okay, so in this case, what's your b sub n to apply this theorem? It's negative 1 to the n plus 1, and then 1 over n. It's just the 1 over n, right? It's the positive part of it, and then the negative 1 just makes it alternate. And that's why I said this could be either n or n plus 1, it doesn't matter. You want that positive thing. So now, does this 1 over n satisfy those conditions? So what's the limit as n goes to infinity of 1 over n? And I'll just, for this one, I'll mark the two conditions that we're checking. So what's that limit? 0. And is 1 over n decreasing? Yeah, and 1 over n is decreasing. So now you're done, right? You got a series whose limit is 0. It's decreasing, and then so the alternating version of it converges. So therefore, this series n plus 1 over n converges by the alternating series test. Oh, I didn't give it a name. This is the alternating series test. eventually we'll just start abbreviating that by 8. Okay? Does that make sense? And so, again, notice this is the harmonic series, but it alternates, right? The original harmonic series without the flipping diverges, with the changing of signs it converges. And so, well, we'll get to another definition here in 1 second. Jot some of this stuff down first. So let's just try this on a couple more first.
So Bob, just like a basic, you can look at this until it converges just because it's 1 minus 1/2 plus 1/3 because the signs changed.
Well, because the sign changes and then it has those other conditions, right, that it's going to 0 and decreasing. You gotta be careful.
Okay, yeah, because it's getting smaller.
Yeah. It needs to go to 0 and it definitely needs to decrease, otherwise you might get some weird jumping around happening. Okay. We'll worry about some more details in a minute. Let's just try some basic stuff here. Basic examples. So the first couple here are ones we've basically encountered before. So if I dropped that -1 to the n on this one, I just have 1 over log n. That was one of the first examples. Oh, I guess we showed log n over n. Well, let's just do this one. So show that this satisfies the conditions for the alternating series test, conclude it converges, okay? And then I'll mention something else about it afterwards. But what's your b sub n in this case? 1 over log n. Show that there's really not much to show, but mention that both of those things are true. Make sense? And I'll say, note. Natural log of n is less than or equal to n. Right, the log function grows really slow. It grows slower than that n function. And so 1 over natural log of n is greater than or equal to 1 over n. What is 1 over n? It diverges, right? And so here's one series that diverges. This one's bigger than it, right? And so this series 1 over log of n diverges. So here's another example where the series without the signs flipping diverges, right? But then once you put that sign in, it converges. And so we're going to talk about absolute and conditional convergence in a minute. And that's really what it's measuring, okay? So some series converge just because the terms get tiny really fast, like 1 over n squared. 1 over n squared, those terms get small really fast. And so it doesn't matter if you add or subtract them. However you add those terms up, you're going to get 0. Whereas things like this, the terms don't get small fast enough to sort of vanish. But if you balance them with adding in some and subtracting out some, you can get to a finite value. Does that make sense? All right. So we'll talk about that more in a minute here. Let's try one, we'll try two more here. All right. So take a minute, try both of these. All right, so let's go through this one here. What did we, converge or diverge, what did you get for an answer?
Converge.
You should get diverge, why?
Because it's not equals to 0.
Yeah, so when you, the first thing you should be looking at, right, is the limit. And in this case, I'll drop the -1 to the n plus 1, but I still take that limit. What's that limit equal? 2/3, right? Now, that's not the series I started with. I have this series. But, so if this goes to 2/3, what happens if I put a -1 in front of it, -1 to the n? It just flips, right, between getting close to 2/3 and -2/3. And so there's no limit at all. Does that make sense? So if this isn't 0, then the alternating version of it can't be 0 either. And so the limit as n goes to infinity of -1 to the n plus 1, 2n over 3n plus 1 does not exist, right? In particular, it's not 0, and so we can conclude that it diverges. That's why the series diverges. What test did we use here? No, well, the alternating series test doesn't technically say that it doesn't diverge. It just says if the limit's 0 and it's decreasing, then it converges. We're actually just using the nth term test, right? We're showing that the nth terms do not go to 0, and so it converges. It diverges by the nth term test, or the test for divergence. Okay. Is that okay?
So when we're finding b of n, did you just, because 2n isn't raised to any power, you just select that and put it over 3n plus 4? You just exclude
The only thing, it doesn't even matter, even if this was raised to the 5th power or to the nth power, that would still be part of your Bn. The only thing you're dropping for your Bn is the -1 to a power.
Oh, is it because 2n relates to 3n plus 4?
Right, well, so it's, remember, it's -1 to the n times something. That's what the a sub n look like, right? And so in that case, right, you should just think of this as -1 to the n plus 1 times whatever's left over, so the 2n has to stay around.
Okay,
Does that make sense?
yeah.
Yeah, everything else besides that -1 should be part of your Bn. Okay. So, now we got this guy. So what's your Bn in this case?
Just tan n over e to the n.
Yeah. Make sense?
Okay, yeah.
All right, so now same stuff, right? Check the limit. What's the limit as n goes to infinity? It's 0. This is one of those things where during the regular semester, I'm like, okay, well, we definitely know by now that this goes to 0, but it was like a day ago that we learned that. But again, what is it? It's a polynomial, right? Divided by an exponential, and you know that exponential is going to grow much faster. If you had to, you do L'Hopital's rule. You get 10 over e to the n still, right? Which definitely goes to 0. But somehow you should confirm that that's 0. If it was, 10 n to the 500th, you definitely don't want to do L'Hopital's rule 500 times to get to the end result, right? But you should still know that polynomial divided by exponential, if you're going off to infinity, will go to 0, okay? All right. So now the next question is that function decreasing? And so the answer is yes, but this one's not quite as obvious, right? Because the 10n is growing, the e to the n is growing, so you got a big thing on the top divided by a big thing on the bottom, they're both growing. And so the fact that it's decreasing isn't sort of trivial like it was on some of the other ones. So you should show some work. And so what I'm going to do is rather than call it b sub n, I'm just going to replace it with x. You don't have to. You can do this. But we did some of these before. And now how do you show that's decreasing? Take its derivative, right? So I should have picked, that's okay. I should have picked something more interesting. This is fine. Derivative is 10 e to the x minus 10x e to the x over e to the x squared, right? Quotient rule. Same thing as before, you can pull out the e to the x, cancel it, and you end up with 10 minus, I'm going to just write this like 10 times 1 minus x over e to the x. And the point is that's less than 0 for x, x greater than 1, right? And so your thing is decreasing. And so 10 to the n, or 10 times n over e to the n is decreasing. And that's all we need, right? The limit has to be 0, it has to be decreasing, and so therefore that series 10n over e to the n converges by the abbreviating here, alternating series test. Okay? So we'll see in the next section, the ratio test, that the ratio test is the much better way to do this problem. It applies really quickly, and we'll get convergence immediately. But anyways, we'll see that as we move along. Let's just plug away here. All right. I'm going to mention error again here, and this time, in this section, I actually do want you to try the error problems in the book. The problems tell you to use a spreadsheet and come up with all these values. You don't have to do the spreadsheet part of it. The book shows you how to do it. If you want to play around with it, it's a good idea. It's useful. It's such a short semester that I don't want to mess around with teaching anything with a spreadsheet to you. So, but you should be able to do most of that problem without the spreadsheet. So do all the pieces that don't involve the spreadsheet, and I'll just say quickly here. Okay, so everything I'm going to write down is assuming we have an alternating series that satisfies those conditions with A sub n is going to 0, and A sub n plus 1 less than or equal to. So you got a decreasing series, or decreasing sequence with the terms going to 0, and then it's the alternating version of it, right? So assume you have that set up, okay? And so if you remember, what was the remainder? The remainder was just s minus the nth partial sum, and so that was just your sum from n plus 1 off to infinity of those guys, right? So it's sort of the trailing edge of your series. That guy was that. And so in this case, okay, I don't want to draw it again. Here, I'm gonna just do this right over this mess that we had here. Remember I had this big number line up here before? And so what did we see? We saw that the value went here, then it came back here, right? And then it wouldn't go any further past that guy from where it came. And so it was like S2, well, where's the real value of S? It's somewhere in here, right? And so S2 is no worse than A sub 3 actually, away from it, right? Because S3 will be over here. That distance will be A3, right? And then we know the actual sum will be somewhere in the middle here. Here's S4, that distance is, that distance is A4. We know we're gonna come back this way. I've lost which way I'm moving now. Yeah, but anyways, the point is you're bouncing back and forth, right? You're never gonna get too far away. And so you can just conclude from that your size of your remainder is less than or equal to the absolute value of the A sub n plus 1, which is just the B sub n plus 1, okay? So that gives you a bound for how bad your error is. And so if you want to find a sum accurate to, 0.001, all you do is figure out what n makes r sub n less than 0.0001, right? And then that, you just add up to there and you'll be in good shape. Okay. So try the homework ones. I think I'll just hold off on that until next time, and you can ask questions, because I'm sure they will throw you off a little bit, but I'll let you chew on it for a minute before we talk about it. Okay, and then we need to get to the last definitions for this section. Okay, so I was saying before that there's two ways series can converge. One way is that the terms get small really fast, and so that as you add more things in, you sort of don't keep building past what you've already added, and you add smaller little pieces on the end. Okay, so that's the first thing. So this series is absolutely convergent if the sum of these converges. Okay, so if I take the sum and I replace the a sub n's with the absolute value. So if your series is positive, being convergent and being absolutely convergent are the exact same thing, right? But if your series has, alternating signs, or some positives, some negatives, then they could be very different things. And this term, or this idea of being absolutely convergent, is measuring the series where they converge because the terms go to 0 very quickly. Okay? And then the next definition is just if this series converges, but is not absolutely convergent, then we say it is conditionally convergent. Okay. Or that's good enough. Okay. So converging absolutely means your terms get tiny really fast. Converging conditionally means that there's some some amount of adding and then subtracting that is making the series converge, and it's not just that your terms get smaller very fast. And so let me just do a quick note here. So let me write this down. So now we're going to see stuff like this: absolutely convergent, conditionally convergent, or divergent. So that'll be what the questions ask a lot of times, determine which one of these is true. So how about this guy? So what's the name of this series again? The alternating harmonic series, right? So if I take absolute values, oh, I need one, n plus 1. If I take the absolute value, all that does is drop that -1 to the end, right? So it'll be just the sum of that, and does that converge or diverge?
Diverge.
Just diverges, it's the harmonic series, right? But we've already seen this one that converges, right? Using the alternating series test, converges by alternating series test, and so this series here is conditionally convergent. Does that make sense? It doesn't converge absolutely, because this diverges, but it does converge. So that's conditional convergence. And so this is where this alternating series test is going to be used most often in this situation to show something's conditionally convergent. Okay, and then let's just do another one here. So we're almost out of time. So let me just do a real quick one. -1 to the +1. Here, we'll just do this one. Straight up over n squared. Okay. So now if I took that same series and I put absolute value around, what do I get? Just 1 over
N squared.
n squared. Does that converge or diverge?
Converge by P series.
Okay, again, converge, and again, P series, P equal to 2, and so that means the original series converges absolutely. So if we move things around, right, I said the definition was absolutely convergent, but converging absolutely, right? Hopefully that all makes sense. So we can tweak the way we word that a little bit. And so the point is, this guy's converging because the terms are getting small really fast, so it doesn't even matter if we took the absolute value, it still converges. Whereas this thing, if we take absolute value, it diverges. The terms don't get small fast enough, but we are adding and subtracting, and so that balance keeps us at a finite value. Does that make sense? All right, and so let me just state one last little theorem here. If, and I'm going to skip any proof of this, but if a series is absolutely convergent, then the series is convergent. And so being absolutely convergent is really a stronger property than just being convergent. And so here, we say this is absolutely convergent, and it's also just convergent, right? You don't have to, if you've shown it's absolutely convergent, then the original series was also convergent. And so this is useful in just a few cases, which would be something like this. So converge or diverge. So sine of n squared plus 1 over 2 to the n. And I'm going to ignore the bounds here. Doesn't matter what I put those bounds on. So is that an alternating series? Sine of n squared plus 1 over 2 to the n? Well, sine is sometimes positive, sometimes negative, right? We know it's cyclical, And so it's gonna bounce around, but it's not clear exactly when that bounces around, right? It doesn't go plus minus, but we know sometimes it's positive, sometimes it's negative. And so the first thing we wanna do is just say this. If I look at this guy, what bound can I put on it? What do we know about sine of anything? It's always smaller than 1 in absolute value, right? Sine's between -1 and 1. So this whole thing is less than that. What do I know about that series here? 1 over 2 to the n. 1 over to the n. Does that converge or diverge?
It gets smaller.
It's that, right? So what kind of series is that? It converges in what? Because it's a geometric series, right? And you're raising a number to higher and higher powers. Converges, geometric series, r equal to 1/2. Does that make sense? And now the comparison test applies. So I got a big series that converges, and it forces this smaller series to converge. Does that make sense? So therefore, this converges by the comparison test, right? The direct comparison test, I guess. And so our original series over T again is absolutely convergent. And in particular, that means it's convergent. Does that make sense? Okay, so that should take care of that section. So if you can, try the homework from as far up as you can get through 12.5. Next time, we're going to talk about the ratio test. And I think you'll find the ratio test to be easier, and you'll like it. And so I hope, I'm going to cover it in the first thing tomorrow, and I hope to just be able to put that on the exam, because otherwise, there's going to be a lot of technical stuff on the exam for the first exam. So let's get through that, and we'll include that. We can answer any questions Friday before the test on it if it's a problem. But I think